Good morning, everyone. Today, inshallah, I will start with reviewing with you and go through the last part in vector spaces. I want you to remember the previous time, we did go through bases and coordinates, and I will continue with that. Just a recap from the previous lecture, it's very, very important. This is one of the important parts in vector spaces, which about bases. I want you all to remember that if I have V be a vector space and B is a subset from V, we say that B forms a basis for V if B simultaneously. Okay, proves just two main things. The first of them is the generating set of V. Number two, linearly independent. So this set of vectors, which is gonna be a basis for the vector space of V, will have to just only prove these two things simultaneously. First of all, successful to be a generating for any vector of V. Number two, this set of vectors must be linearly independent, as we spoke in the previous sessions, as I told you before in the previous sessions. If a set forms a basis for a vector space, the order in which we consider the vectors in the set is relevant. This is really very important. Once you put these vectors, there will be coordinates down the road related to these vectors, so they should be kept in order. Another remark that the dimension Rn, which is the number of vectors that exist in R. So if I'm talking about R2, the basis will be two vectors. That's the standard or the optimal basis developing R2. If R3, so you will have three vectors forming this vector space and so on. If I have a matrix m by n, so the general dimension is gonna be m times n. And also we did go through this in the previous session. To the basis of Rn, which formed by the vectors e1 to O, e1 to en, which we mean by the standard basis of any vector space, which is really very simple. If we are talking about R2, so the standard basis is gonna be 1, 0, 0, 1. If we are talking about R3, for example, so it's gonna be 1, 0, 0, 0, 1, 0, 0, 0, and 1. And this is the generalization of this rule. So this is for R2 as I told you, and this is for R3. We can call them the standard basis of any vector space. Whatever the dimension is, depending on the dimension, you will start forming the columns of a unit matrix, as we said before, relative to this dimension, and these columns will represent this set of vector bases for this vector space. Also, it's famous to call them the canonical basis of Rn. Okay, one extra thing, it's about the linear combination. Let V be a vector space and the beta a basis of V. If V any vector in the vector space V, then there is one and only one linear combination of this vector in V, which is equal to V. So now we are talking about the coordinates. Of course, all of us, remember that I can form any vector with respect to R or belongs to R simply by finding the set of coefficients of this linear combination. So V can be simply C1 times U1 plus C2 times U2 plus C3 times U3 and so on, depending on the dimension of your vector space. So if I'm talking for simplicity and for a good representation for R3, for example, so any vector was equal to R3, and we can form it simply by multiplying C1 times U1, C2 times U2, C3 times U3, where the basis of R3 are U1, U2, U3. These coefficient values, we call them the coordinates, and we can write them at this form. This is the vector V, which is taking the basis B, which is gonna be, those coordinates are C1, C2, and C3. This is actually the coordinates. So it's written here, let V be a vector space, beta, which is the set of vectors that belongs to beta, as an order set, a basis of V, and U, a vector of U, of V, to the scalars which give the equality. U will equal to C1 V1 up to Cn Vn if we are talking about Rn dimensional space. We call the coordinates of U with respect to basis P, and we write them as you can see. It's really very simple, and we also did go through it. For this example, just to refresh your information, and also to show that the importance of the standard coordinates, okay, and the standard basis for any vector space. Here, it's written that write the vector 1, 2, 3, which belongs to R3, and the linear combination of the vectors of the basis of R3. And you have given two bases for R3. One of them is the standard base, which is 1, 0, 0, 0, 1, 0, 0, 0, and 1. And it's required to write. This is really very simple. I want you to know that if you are asked to find a vector using certain coordinates with respect to a basis, all you have to do is to get this vector using this formula. And once you get your vector, you can write it on the canonical form or the standard form. So simply remember, if I want, and also this is, we did go through this in the previous session, but I want you to remember it. It's important for our continuation. So if I want to simply write 1, 2, 3, okay, as a linear combination from the subvector space, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, all I have to do is to say that vector V is simply 1, which is the coordinates, times 1, 0, 0, plus 2, which is the coordinate or the second component of this vector, times 0, 1, 0, then finally plus 3 times 0, 0, and 1. What I've wrote here is considering the coordinates of the vector by itself, 1, 2, 3, at the coordinates of the standard basis. So, if you are asked to find the coordinates of a certain vector with respect to the standard or canonical basis, all you have to do is to get the coordinates and of the vector, and they are exactly the same like the coordinates of the vector with respect to the vector space. What I mean is, you will see down the road with the next problems. But if I want to find the coordinates that satisfying the base subvector, the base for the subvector beta, which is a subvector space, 1, 0, 0, 1, 1, 0, 1, 1, all I have to do is to solve the system, which is A times X equal the value of the vector that you are interested in. X here represents the column of the coordinates that you will need to form V with respect to A. So if I want to find these coordinates, all I have to do is simply either to multiply this equation by A minus 1, which is the inverse of the A matrix, which formed from the columns of the vector space given here, or to solve it using algebra. Both of them are completely fine. Let's go through it just to a quick reminder. I will take the vector of the first vector in this basis of beta, which is 1, 0, 0. The second vector, which is 1, 1, and 0. The third one, which is 1, 1, and then I will insert them in this augmented matrix with the results, with the result of the vector that I want to find its coordinates. Simply start working your magic, going through the echelon process. So simply it's gonna be 1, 1, and 1, and the value is equal to 1. The second row starts with 0, then 1 and 1, 2, multiply, and the third one also is already adjusted, which is 0, 0, 1, and 3. I will need to adjust the second row, and this is easily by multiplying by -1 on this row and then adding on the first row. So -1 plus 1, it's going to change this value to 0. -1 plus 1, so also it will change it to be 0. -2 plus 1, so it's going to be -1. In a similar manner, I can multiply the third row in -1 and the adding on the second row. So -1 plus 1, the result will be 0. -3 plus 2, so the result will be -1. And then now I have the coordinates. So I can write that with respect to the beta subvector, I can write vector v, but with respect to the basis of b, the coordinates are simply will be -1, -1, and 3. This is for C1, this is for C2, and the last is for C3. So simply, if I use this combination with this basis, I will have the vector which is 1, 2, 3. It's really very simple to show that. Just only I will write -1 times 1 and double 0 minus 1 times the second vector, which is 1, 1, and 0, and finally plus 3 times the vector, which is 1, 1, and 1, and the result, you will see this is -1, this is -1, this one is -2, plus 3, so it's going to be 1. The second one also, it's going to be 0, then you will have -1 times the second, which is 1, it's going to be -1 times 0, it's okay, done. -1 times 1 is -1, plus 3, which is going to develop 2, and finally -1 times 0 is 0, -1 times 0 is 0, 3 times 1, which is going to be 3. And you can see that we succeeded in getting the vector v as a linear combination from the basis of b. So it's really very simple. That's, you can see now. Now we can get vector 1, 2, 3, as I told you, from the first basis. It's very, very simple. So 1 times 1 double 0, 2 times 0, 1, 0, 3 times double 0 and 1, and which is unique. If I want to get the combination of the coordinates C1, C2, C3, which will develop 1, 2, 3 from the basis of B, simply all I have to do is to solve that system, or to get the inverse of the A matrix. This is the A matrix. Okay, this is the A matrix, which is the matrix that I can get simply from the basis of subvector beta, the first vector, second vector, third vector. Work your magic with row operations, and then finally you will find the values -1, -1, and 3, and now you have a unique linear combination to develop 1, 2, 3. Those are the coefficients, as we said in this example. That's to get the vector beta from the basis of vector space. All I have to do is to use this linear combination. Also in a similar manner, and we did solve that previously, and this is the questions that I want to focus on. Stating here, what are the coordinates of V with respect to basis B? You need the coordinates of V with respect to basis B. This is really very simple. All I have to do is to use, similar to this manner, exactly the same. I will start by forming first the system of equations, which means that I have C1 times the first vector, C2 times the second vector, and C3 times the third vector, which is supposed to equal to 12, 15, and 19. I can solve this system exactly like this problem for C1, C2, C3, and this way I can find this combination, which if I used with these three vectors, I will get the required vector, which is 12, 15, and 19. This is exactly done. These are the equations. On the augmented form, I can find C1, C2, C3, or as I told you many times previously, can simply get the inverse of this matrix, then multiply it by 12, 15, and 19, and voila, we got the coordinates, which is 1, 1, 1. So I can write now the vector V with respect to beta will equal to 1, 1, and 1, and this is the linear combination or the coordinates that we can, by which we can generate vector v. Also here, it's stating that what are the coordinates of u with respect to the standard basis of R3, knowing that these are the coordinates. And that's the question that, or the matter that I want to focus on. Here, he's asking you for what? Let's read it once more. What are the coordinates of u? So, he's mainly asking you about the coordinates of vector u. Okay, with respect to the standard basis of R3, knowing that these are the coordinates that that you have at the time being. Actually, this is a twisted question. Mainly, he's asking you to get the vector, which is v or u, whatever. I'm getting the vector u using this linear combination from the beta space. So simply multiplying 1 to 1, just a second, I will need to go through it. So now you have the coordinates, you already have the coordinates of this vector that's gonna build this vector, which are 1, 2, and 1. And I need to get this vector first. So simply, all I have to do is to do the system of equations that I told you about. All I have to do is to get the A matrix, which is required about changing the vector spaces, or the A matrix, which is simply formed from the columns of the vector space. So it's simply 1, 2, and 3 for the first vector, 4, 5, and 6 for the second vector, 7, 8, and 10 for the last vector, 7, 8, and 10. I will multiply them by the coordinates. Now what I'm doing is that I'm getting the vector u. So this is mainly the coordinates, and this is the column of the coordinates, and this is the A matrix. So if I multiply them together using this combination, which is simply 1, 2, and 1, I will get the values of u. It's exactly the same, like taking the first vector, which is 1, 2, and 3, and multiplied by C1, and 4, 5, and 6, multiplied by the second value of the given coordinate, plus C3 times the third vector, which is 7, 8, and 10, and you will have your vector exactly like this setting. So either to use the main formula or to use this matrix form. Okay, and anyhow, 1 times 1 equal to 1. This is going to be 8 plus 7. So you have 1 plus 8, which is 9, plus 7. I believe this is 16. Similarly, like, please be with me. I usually do a lot of stupid mistakes. So 2 times 1, 2. 5 times 2, which is 10. The sum is 12, I believe, plus 8. So this one comes to 20. 3 times 1, which is 3. 2 times 6 is 12. The sum is 15, plus 20, so it's 25. Now I have this vector. And it's exactly the same. If I want you to find the coordinates, but with respect to the standard basis, because simply this vector can be written as a linear combination, okay, as a linear combination from the standard basis of R3, which is simply 16 times 100 plus 20 times 0, 1, and 0 plus 25 times 00 and 1. And this way I can get the coordinates, so I can rewrite that thing as the vector u with the coordinates relative to the standard vector space, which is simply R, 16, 20, and 25. So both of them are the same. يبقى once more in ARC, لو اتسألت انك تجيب فيكتور ومديلك اللينير كومباينيشن بالنسبه للفيكتور سبيس تاني بيتا، كل اللي عليك تعمله انك تاخد الكومباينيشن وتبدا تضربها في الفيكتور سبيس بتاعك او السب فيكتور سبيس او البيزس you will get your vector. طيب it's exactly the same بالظبط زي مطلوب منك انك توجد الكوردينتس but with respect to الستاندرد بيزس. بجيب الفيكتور بعدين بقسمه طبعا للستاندرد فيكتور which is 1 0 0 0 1 and 0 0 0 1 exactly like this. Okay, here you go. Okay, it's written in this problem, it's given the coordinates which can be used with the basis of R3 to get a new vector and from which we can find the coordinates of this canonical basis. Exactly like what I told you, this is the form of the vector which is 16, 20, 25, which can be easily written as 16 times 1 0 0, 20 times 0 1 0 and 25. So this is the vector, and if you want to write it, as I told you, as a coordinates, this is the coordinates. Okay, perfect. Okay, exactly the same. So I will skip this problem. It's similar to what we did, just to go through it. So it's gonna be the same. Now, as I told you, all the previous slides, we did go through it in the previous session, but I want just to go through it to shed the light on all the steps that we did. We will need it a lot in this lecture. Also, by the start of this slide, same way like I will go through the remaining definitions. Okay, just wait a second. Okay. Here we go. If beta is given, okay, this is the summary of the previous problems. If you want to see how beta is formed, this is if you are asked to get a vector using a certain set of coordinates, I will use beta. If you are asked to find the coordinates, I will use the inverse of the matrix formed from the vector subspace, and this is mainly the main formulas that we want to go through it. I will skip this part, it's exactly the same like the problems that we did go through it, and you will find all of this in the previous session. Okay, just wait a second, because all of these slides we did already go through it. Okay, just a second. Yep. Okay, I did go through this slide, also that one too. Yes, okay. Let's start from here. Yep. Okay. Yes, just a second. I will start from this slide because the previous slides we already did go through it in details previously, and I believe the session that I spoke with you for the time being covered all the ideas that I want you to see. Now I want to talk about the orthogonality between two vectors. It's very, very simple. All you have to do is to, if you want to check if you have two vectors orthogonal or not, you have to do the dot multiplication. Simply, as we saw previously, we multiply x1, the first coordinate for the first vector, times the first coordinate of the second vector, and plus the coordinate of the first vector, times the second coordinate of the second vector, similarly like plus multiplying the third coordinate of the first vector, times the third coordinate in the second vector, the sum will equal to 0. Check if these vectors are orthogonal or not. It's really simply. All I have to do 1 times -2, 2 times 1, 3 times -4, 4 times 3, and the value will equal to 0. So this means that these two vectors are orthogonal to each other. We explained this slide, and also this part was covered previously, but just wanted to go through it to make all this work together in the coming slides. Our orthogonal complement of S, if this S represent a vector space, the orthogonal complement are the set of vectors which are perpendicular on all the vectors that exist on S, and this is called the orthogonal complement of R3. Every plane of R3 passing through the origin is a subspace of R3. So you have now each vector space, subvector space that passes through the origin, and also the orthogonal complement of S are the orthogonal set of vectors, okay, are the orthogonal set of vectors in the plan. They can also form a vector space. Simply, all the vectors that can go through the origin of these subvector spaces and the orthogonal complements on these vector spaces are also vector spaces. Now we can come to the fact, if I want to, if you have W be a vector subspace of Rn, the orthogonal complement of W in Rn, this is the symbol that we are going to deal with, which is W perpendicular on the set of all vectors which are simultaneously orthogonal to all vectors of the vector W, and it's written that omega t is the set or the subspace of all vectors belongs to Rn, such that once you multiply them by all the vectors in the main vector space, the result will equal to 0. Okay, here it states that what is the orthogonal complement of omega, which is a subvector space from R3, and the span is given by 1, 2, 3. If I want to do this, it's very, very simple. We already did that before. I will assume that the orthogonal vector space is going to be x, y, z. So I will have x, y, and z, which is a perpendicular vector or orthogonal vector on 1, 2, 3 times 1, 2, and 3. And all the vectors that present in this subvector space are simply k times 1, 0, which equal to 0. I can divide this equation, which is simply an equation, I can divide on k, which is a scalar value, such that k belongs to R. So if we did that, we will have x, y, and z times 1, 2, 3, that's a dot product between vectors, and equal to 0. And here is the condition for the orthogonal vector space on 1 to 3, which is going to be x plus 2y plus 3z must equal to 0. And that implies that x must equal to negative over 2y minus 3z. I will simply take this fact and sub in the coordinates of the orthogonal complement, which is xyz. So it's going to be, instead of x, I will use negative 2y minus 3z. This is y, and that's z, which is simply, as we did before, we can find the vector basis of the orthogonal set of vectors from this equation simply by writing it in this manner, which is negative 2y minus 3 over z. The second coordinate will be y plus 0 times z. The last one will be 0 times y plus 1. In this manner, I succeeded in separating this compacted form into two parts which depend on the values of y, and the other one which depends on the values of z. And simply, I can rewrite this form to be as the following one. Negative 2y, just separating the y's from the z's, negative 2y, then I will have y, and finally I will have 0 times y, which is simply can be added on negative 3 over z, then 0 over z for the second coordinate, and finally for the z. I can take z and y as commons, so y is going to lead to negative 1, negative 2, 1, and 0, then plus I will get z as a common, so I will end up having negative 3, 0, and 1, and so the span of the orthogonal set can be simply written as the first set of vectors, which is negative 2, 1, and 0, and the last one is negative 3, 0, and 1. If you remark, this is the span of the orthogonal complement on the span W. So this is the vector space which is represented by 1, 2, and 3. Now I have what's called omega orthogonal part. Remark the dimension. The dimension of omega is 1. The dimension of the orthogonal complement is 2, because you have 2 vectors. Once more, let's go through it quickly on the slides, stating that to determine the orthogonal complement of omega, we already know that any vector of W will be on the form of K, 1, 2, 3, okay, on the form of K, 1, 2, 3. So all I have to do is to get omega orthogonal, or orthogonal set of orthogonal complements, which are xyz belongs to R cubed, such that xyv times K, 1, 2, 3 equal to 0. For every K belongs to R. So simply, all I have to do is to work on this formula, which is xyz times K times 1, 2, 3. I will divide on K, so you will have simply x times 1, y times 2, and then times 3, which where you can get the condition for the formation of xyz, which is the main vector for the basis of the orthogonal complement. All I have to do now is to replace x by negative 2y minus 3z, which is already done, and start separating the values exactly like what we did here, exactly. This is negative 2, 1, and 0, and this is negative 3, 0, and 1. These are the 2 sets of vectors that form the orthogonal part or the orthogonal complement of the vector space omega. I want you to remember that the dimension, and we will talk about this shortly in the next slide or so, that the dimension here is 1, the dimension here is 2, the sum of them will give you the dimension of the vector space that we are talking about. This is the statement that states exactly what we saw right now from this example, that the dimension of W was the dimension of the orthogonal complement. Once you add them both together, you will have N, as you can see. We're stating that as a confirmation, and also I said that in the previous session. If I want to get the orthogonal complement of W, which is only span of 1, 2, 3, and 4, 5, 6, all I have to do is just to take advantage from the dot product of a vector and its orthogonal complement. So I know now, if I multiplied 1, 2, 3 times K, which times xyz for the orthogonal complement, it will be equal to 0, and same way like for 4, 5, and 6, if we multiply xyz times 4, 5, 6, the result will be 0, and this will lead you to a system of equations, 2 equations and 2 unknowns. I will try to solve this system the way you like it, either using Gauss-Jordan, whatever, or using the inverse method, or whatever you want to do. But here it's not going to work. I will have to use the echelon form. So I'm using 1, 2, 3, 4, 5, and 6, solving this homogeneous system of equations, which come to this form. I will multiply by negative 4, then adding with 4, as you know, it's going to be 0. Negative 4 plus 5 is going to be 1. Negative 4 times 3, which is going to be negative 12, plus 6 is going to be negative 12. And then I will go the extra step after getting 1 as a pivot, multiply negative 2 and adding on the first row, I will end up having this form, which implies that x will equal to negative, x will equal plus x minus z equals 0, and y plus 2z equals 0. And in this manner, I will succeed in getting x as equal to z for the first coordinate, and y equal to negative 2z. Now I can write the orthogonal complement, as you can see, okay? It's exactly like the previous slide. Now I will change x was equal to z, and y which equal to negative 2z. Once you do this, you can isolate z as a common, as we did previously. So you will have z1 minus 2 and 1, such that z belongs to R, and so the basis will be 1. Remark, what should be remarked here, is that we started with these 2 vectors, which are the basis of the main vector space, and we ended up having this orthogonal vector, or which belongs to the orthogonal complement of the first vector, the dimension here was 2 and the dimension here is 1. This is confirmed here, dimension of omega t, which is 1, equal to R3 minus 2, and you will have the same as a statement and confirmation on this relationship. Okay, exactly the same. As I told you, now I want to talk in specific, this is the new part in this session, and I want to go through the null, row, and column space in specific. What we mean about the null, row, and the column spaces, I will have to go or remind you all with what we mean about solving a system of equations. Let's see. Remember, in a solution of a system of homogeneous set of equations, if you have ax equal to 0, now you have just only two possible cases. Either to have that the solution set is the trivial solution, which means that x is all equal to 0. And remember, this is the way I used to use in order to check if you have a bunch of vectors, if they are linearly independent or not. But now, for the time being, I'm trying to solve a homogeneous system. So if you are trying to solve this system, you will be between two alternatives. The first of them is to get x equal to 0. It means you will have once you work with the issue of 4, you will succeed in getting a unit matrix which reflects that x1, x2, x3, if we are talking about a 3 by 3 system, equal to 0. So all of them equal to zeros, x1, x2, and x3. Okay, or you may have infinite number of solutions, which is a vector space by itself, which is the vector space of the solutions of this system of equations. And we can get a generating set representing this relation between variables. So maybe if you are trying to solve a homogeneous system of equations, as I told you, you will be between two things, either getting x1, x2, x3 equal to 0, which is the trivial solution, or get a relation